Thank you, guys. Good afternoon and welcome from sunny California. It's just dawn here, and I'll be talking a little bit about a brief history of router architecture. So the point of this talk is education and history. I'm not going to be naming names. Everyone, and I mean everyone, messed up at some point. So it's amazing that the industry is still here. Lots and lots of companies failed in doing this, and I'm not out to make anybody's life miserable. All of this is from my memory. All the mistakes I make are all mine. No sources are used here, so it's all just history. In the beginning, router architecture, well, it's just based on simple old computers. You take a bus, you plug in a CPU card, you plug in a memory card, and you plug in a bunch of NICs. And as you might imagine, while this makes for an okay computer, it makes for a really lousy router. The bus is a constraint, the CPU isn't fast enough, the memory gets oversubscribed, and your router just doesn't do very much. Every byte passes through the CPU twice. You have a packet, it comes in the NIC, it goes through the CPU, it goes out to memory, you decide what to do with it, you bring it back through the CPU, you shove it back to a different NIC. You're very capacity limited. And all of your infrastructure costs, because all of it is maximized day one, well, that's very painful because it means your box costs a lot and it's not really economical until you fill the box. This is not a good scaling property. You want your costs to be proportional to the bandwidth you're delivering. So that sucks. Okay, well, the bright idea was one bus is killing us. Let's add another one. No, this doesn't help much anyway. Sure, the second bus is 10 times faster, but it's got the same architectural problems. Now, you can add an ALU, and that one turns out to be a digital signal processor. It gives you fast, cheap CPU cycles, and that's efficient, but more bandwidth and more cycles, you really haven't changed the architecture. And this gets you along for a little ways, but it still sucks. Okay, well, what can you do to make this better? Well, okay, we're spending a lot of CPU cycles doing route lookups, and we can probably do that a better way. And this was the birth of custom silicon, so we can take an FPGA, field programmable gate array. This is a predecessor to an ASIC. And we can teach it how to do longest prefix match. And if we do that, we can get maybe a little bit more cycles back. But it turns out that this is not rocket science, and it's a lot of effort, and it makes things better, but it doesn't double the speed of the box because guess what? All the other overhead is costing you more than just longest prefix match. So the good news is you can forward packets using silicon. So management took a look at this. Maybe we should build routers using ASICs. And management looks at this and said, no, CPUs will save us. Now, looking backwards on history, do you think you could build a router with CPUs today? No. It turns out we did the wrong thing. And that took a long time while we figured that out, unfortunately. It took us a long time. It was very painful because the cost of building the ASICs was then very expensive. It took a long time for people to turn around, make the investment in ASICs, and come back and doing the right thing. So to be scalable, the processing and the bandwidth must be distributed, and we have to add it incrementally as we add capacity. Along came the web, and this changes everything. So ARPA, the original ARPANET folks, decided to get out of the business. And they asked the National Science Foundation to take over the network. And the National Science Foundation said yes, and they funded a backbone. And they did not want to run all of the network, so they went to a number of academic universities, asked them to set up regional networks. And those regional networks are now well known in ancient history. One's based around Stanford and MIT, University of Maryland, several others. They started buying routers and setting up networks. And then the web came along and the carriers bought them, right? The telcos, at the time we had multiple telcos, and the telcos bought the NSF-net regionals. So then real money came into the equation, and that's when the industry changed. There became a lot of competition for building routers, and part of the investment in ASICs comes from that. I should note that's about when Juniper started. All right, and let's see, the next iteration was the scheduled crossbar. And this is an interesting idea. This is starting to get to something scalable. You've got multiple inputs you see here and multiple outputs. And if you're very careful, you can figure out about when you're going to send packets from an input to an output. Now, this looks like it's a bit of progress, and indeed it is, but it's not ideal. It turns out it's still got lots and lots of problems. It gives us distributed processing and bandwidth, but the scheduling problem turns out to be very hard, and you've got contention for output ports. So your switch lanes need more bandwidth than you have on output, and that means you have to have speed up. And that's expensive. You're paying for a little bit more infrastructure than you strictly need. And you can't always drain all of your inputs. So you end up with head-of-line blocking. And we saw multiple instances of multiple boxes with this problem, and it was not pretty. What you'd really like here is a queue for each output on each input. But that means you have n output queues, and that's extremely painful. Still doesn't scale very well. Okay, well, you could start a company here and you could build a distributed cell memory and a full mesh. And we won't talk about who started this. And this has some interesting properties too. Okay, now it's nice. You've got scalability. You've distributed your processing and you've distributed your bandwidth. Those parts are pretty good. But as it turns out, you've got all NICs that are dependent on all other NICs. So you hot swap one of the cards and you drop all traffic throughout. And the bandwidth of the system is a fixed multiple of the bandwidth of the card. So you can't build out to bigger and bigger systems. This first system you build is the biggest you could build. And that's not very scalable. Okay, not happy, not wonderful, but forward progress. And then around 2002, we have NLNOG. Happy birthday. Next crazy idea that people tried was a torus. And I can't even draw one of these, so I have to cut and paste this. So it turns out that donuts make very lousy routers. Strange traffic patterns can cause strange patterns in your fabric, and that causes congestion in the backplane, and bad things happen. Your links are still finite. So your bandwidth, when you distribute it, it needs to be uniform. If it's not uniform and your traffic pattern doesn't match, well, you're going to have a problem. Speaking of starting your own company, you could build a box that had centralized shared memory. And this has lots of problems too. You can't make it a single bank of memory, so you have to do tons of things with lots of memory controllers. And now you need an interconnect for the memory controllers. And you've got all the same problems all turned over again, and it still doesn't scale very nicely. And your memory bandwidth is bounded. You haven't distributed everything nicely. It still sucks. Oh well. Finally, around 2004, we got to something sane. And this is a 5-stage CLO network. And this is the internals of a big router. You see 4 inputs on the left, and then a CLO network in the middle, and 4 outputs on the right. The nice property here is that this architecture is rearrangeably non-blocking. So we've distributed our bandwidth, and even on link failures, you can rearrange and redirect cells so that it flows through the network without a problem. No bad blocking problems, no head of line blocking if you're careful. Now, if you take a look, this architecture is symmetric around the dotted line you see in the middle. So you can actually take this architecture and fold it at the dotted line, fold it so that the inputs and the outputs come back to each other. And then you get a folded 5-stage CLO network. And that's where you put your NICs, and now you've got a router. This is something that scales. Our bandwidth is distributed, uniform, and redundant. Now, there's still scalability challenges. You still need a queue per output. Your cell addressing is finite. Your fabric can only be so big. The cell fabric turns out to be proprietary. If you want to do a technology upgrade, it's very difficult to change. If you want to change the fabric, you end up changing the entire chassis effectively, all the cars in the chassis to do it. Pretty much a forklift upgrade. Vendor lock-in and chipset lock-in are still issues. Now, the good news is this is not new work. A guy named Charles Clough figured this out. He did it in 1952. It only took us 50 years to figure it out. Oh well. Now, this architecture should look familiar. This is what modern data centers look like. A layer of leafs in top of rack switches, and a number of spine switches. And if you go one more level, you sometimes have super spine switches. This should seem very familiar. Yes, what we've learned is that we don't have to keep our fabric internal to the box. We can take our fabric and we can build an external fabric. CLO topologies are still the right answer. We just want to do it externally. Trying to build and scale one box is too expensive. Even if we want to do a multi-chassis system, it's too difficult. So what we've learned is we really, really like going to a multi-box CLO fabric. What can we see as the future? Well, we have elastic scaling. We continue to use this CLO topology. And it's really nice because it's scalable in 2 dimensions. We can add more spines, or we can add more stages. We could have super spines if you want, or more stages after that. We've got easy incremental upgrades. You can actually upgrade any single box in this architecture without a problem. Since we can now do everything with standardized Ethernet, it's fully vendor independent. You want to buy one box from one guy and another box from another guy? No problem. It just works. It's all Ethernet. It's all packet-based. It's not cell-based. So the downside here is that it does need a little more bandwidth. But the bandwidth is cheap. This is easy to fix. What is it missing today? What we really need is management plane abstraction. If you're building one of these networks today, you end up managing lots and lots of boxes. If you were managing a multi-chassis, it would look like one box. What we really need is a management plane that allows us to manage an entire super spine network as a single box. Challenge for another company. We've seen people start doing this with a deaggregated core. They take a chipset, they say, we're going to build it out of white boxes and we're going to give you this. But they do it as a multi-chassis, so it's one single software architecture. Well, you've still got the same underlying chipset, and you've got chipset lock-in, and now because it's the same software in all boxes, you've got software lock-in. Vendor lock-in is something you want to avoid, so maybe this is not the right answer. And that's where we are today. Are there any questions?
Well, first there is applause, Tony, as you heard. People have been sitting here watching your presentation as if they were being told the story that they had been waiting for their whole lives. For me, this partly answered questions. Well, a question that I had in my mind for years. If I look at a network and it forwards millions and millions of packets per second, and for each packet, this router has to look up again what is the destination and where does it need to go and how should I handle it. Isn't this amazing technology, people? Millions of packets per second, tens of millions, hundreds of millions of packets per second. And now, Tony, in your presentation, you have shown how the traffic actually goes through the router. Is there something you can add and tell me and the rest of the audience a little bit about how the system actually manages to find the best destination for all those millions of packets per second out of those million destinations that are there in a full BGP router and still just work? I mean, it's amazing. How does it work?
There's no rocket science here. We are getting a little bit of echo. So as you know, the routing protocols carry all of the routes, and the output of the routing protocols is the RIB and FIB, and the silicon, once we get the FIB downloaded into the silicon, it takes over, and it's capable of doing all of the speed. We now have massive parallelism inside the silicon, so that's how all that magic happens. Basically, any of the ASICs that you see on the market today effectively have hundreds of forwarding cores. And that's how all of that happens. And a lot of people put in lots of hard work and try and make that actually fast and efficient.
Wow. Thank you. There is a question from the audience. Blake is at the microphone.
Blake Wazeo, thanks a lot for this. It's a really great high-level overview of router history. If we say that the current state-of-the-art of congestion management in a router chassis is virtual output queuing, do you see anything on the horizon that might be better or potentially replace that?
Not anytime soon. Virtual output queuing has done a pretty darn good job, and I haven't seen a whole lot of cases where there's a problem.
Thanks.
Thank you. Are there any other questions for Mr. Tony Lee? Any feature requests? All right, then I will say once again, thank you very much, Tony, for joining us. It has been an honor and a pleasure of having you in our NLNOG Day. Thank you.
Thank you, guys. Happy birthday, NLNOG.